The USS Nautilus is 500 miles from the North Pole, sealed under a ceiling of solid Arctic ice. There is no surface to return to. If anything goes wrong with the air the crew is breathing, mechanically, chemically, catastrophically, there is no emergency exit. 116 men aboard weren't worried about running out of oxygen, because for the first time in history, a machine on this submarine was making its own air, faster than the crew could breathe it.
Humans have tried to go underwater for thousands of years, but every early attempt hit the same wall. Air runs out. You can hold your breath, or bring air down with you in a bag or a bell, but sooner or later, you have to come back up. For centuries, that limit didn't change, until one obsessive, broke, self-taught engineer in 19th century Spain decided to solve it. Not to win a war, but to save coral divers from drowning. His name was Monturiol, a lawyer-turned-inventor who watched a friend die in a diving accident and decided no one should have to risk that again. He built a hand-cranked submarine called the Ictinio. It worked, but it was painfully slow, powered by nothing but human arms. Monturiol needed an engine, but an engine that burns fuel needs oxygen, and there's no oxygen to spare in a sealed submarine. So, how do you power an engine underwater without stealing the crew's air? Monturiol's answer in 1867 was almost unbelievable for its time. A chemical reaction that produced heat to drive a steam engine and released oxygen as a byproduct which the crew could breathe. He'd built the world's first air-independent submarine engine nearly a century before anyone else attempted it. His submarine, the Ictinio II, actually worked, and then, almost immediately, it was gone. Monturiol ran out of money. His creditors seized the submarine and scrapped it for parts in 1868. The man who solved underwater breathing 100 years too early died in obscurity. His idea, though, didn't die with him. It would resurface almost a century later on the other side of the world for a very different reason. By World War II, submarines were finally practical war machines, but they hadn't actually solved Monturiol's problem. They just found workarounds. Crews carried compressed air in steel tanks and bled it into the boat as needed. When things got desperate, like hiding on the seafloor while enemy destroyers hunted overhead, the crew would compress their own stale, vitiated air from one end of the sub into empty tanks at the other end, just to buy a few more hours. This created a genuinely miserable side effect, swinging cabin pressure that left crews with headaches and ear pain on top of the stress of combat. And there was a hard ceiling on how long any of this could last. By the mid-20th century, engineers had pushed diesel-electric submarines about as far as chemistry and compressed gas would allow. Roughly 25 days submerged, and that was the absolute edge of what was survivable. Every submarine on Earth had the same fundamental limitation. Eventually, it had to surface. Not because the crew ran out of food or fuel first, but because it ran out of air. Solving this wasn't just an engineering problem anymore. It required a source of power that didn't exist yet. That power source had a very specific champion, a Navy engineer named Hyman Rickover. Rickover was notorious, demanding, relentless, and convinced that nuclear reactors could do more than generate electricity on land. He believed a reactor could go inside a submarine, and in doing so, remove the 25-day barrier entirely. Here's why that mattered so much for the oxygen problem specifically. A nuclear reactor doesn't burn anything. It doesn't need air to run, unlike a diesel engine, and it produces enormous continuous electrical power, which meant, for the first time, a submarine could run something power-hungry non-stop, an electrolysis unit splitting seawater into hydrogen and oxygen indefinitely. Rickover pushed this through years of institutional resistance and skepticism. In 1954, the keel was laid for a submarine that would prove the concept, USS Nautilus, the world's first nuclear-powered vessel. It wasn't just faster or stealthier than anything before it. It was the first submarine that could, in theory, make its own atmosphere forever, limited only by how much food it could carry. Nuclear power on paper is one thing, but in 1958, the Navy decided to test the entire concept in the most unforgiving place on the planet, underneath the Arctic ice, all the way to the North Pole. It was codenamed Operation Sunshine, and it was ordered personally by President Eisenhower, kept so secret that most of the 116-man crew didn't know their real destination until they were already at sea. This mission made the life support problem non-negotiable. Under solid pack ice, there is no surfacing in an emergency, not for hundreds of miles in any direction. If the atmosphere systems failed, there was no plan B. Commander William Anderson gave his crew one last chance to walk away before they left Pearl Harbor. Not one of them did. For 4 days, Nautilus ran completely submerged beneath the ice, its mechanical CO2 scrubbers pulling stale air clean, and its electrolysis system continuously replacing the oxygen 116 men were burning through. On August 3, 1958, Nautilus became the first vessel in history to reach the North Pole, underwater, powered by a reactor, breathing air it had made itself the entire way. It wasn't just a geography milestone, it was proof that Monturiol's century-old idea, an engine that makes its own breathable air, finally worked at a scale that could keep well over 100 people alive indefinitely anywhere in the ocean. Here's where this story takes a turn a lot of people don't expect. Submarines weren't the only place engineers needed a backup way to make oxygen fast without power. The solution, devices called oxygen candles, solid chemical canisters that release breathable oxygen when ignited, had been used safely aboard Soviet and Russian submarines for decades. Eventually, the same technology flew to space aboard the Mir space station. By February 1997, these oxygen candles had been used successfully more than 2,500 times aboard Mir without incident. Then, on February 24th, cosmonaut Alexander Lazutkin activated a routine canister, and it ignited into an actual flame, throwing molten metal across the module and filling Mir with thick smoke. The fire blocked the crew's path to one of their 2 escape capsules. 6 people were trapped in a burning module with no way to open a window, no way to step outside, fighting a fire that fed on the same oxygen they needed to breathe. They put it out with extinguishers, and the ship's systems slowly cleared the smoke over the following hours. No one died, but investigators later found the likely cause. A scrap of glove material had accidentally ended up inside the canister, and under the right conditions, that was enough to turn a life support device into a blowtorch. This is the uncomfortable truth engineers had to sit with. The exact same chemical reaction that reliably keeps people alive thousands of times can turn dangerous if a single manufacturing step goes wrong. It's why every oxygen-generating system on a modern submarine or spacecraft is wrapped in redundant sensors, containment procedures, and strict manufacturing controls. Not because the core idea is flawed, but because they learned, the hard way, exactly how it can fail. Today, every nuclear submarine on Earth still runs on the same basic principle Rickover proved in 1958: a reactor, an electrolysis unit, and CO2 scrubbers, running continuously so a crew can stay submerged for months rather than weeks. And the ISS still carries oxygen candles as an emergency backup to this day. Redesigned after the Mir fire, but built on the same chemistry Soviet submarine engineers relied on for decades before that. It's a strange thread to pull on, an idea from a bankrupt 19th century Spanish inventor, refined under Cold War pressure inside a nuclear submarine, tested to its limit under the polar ice cap, and eventually carried into orbit, where it nearly started a fire 250 miles above Earth. Every time humans figure out how to survive somewhere air shouldn't exist, it's built on the same discovery. You don't have to bring your air with you. You can build a machine that makes it.